All right, Calculus 12, here we go. This is going to be for our 2020 year, our last lesson. Just the way she worked out, we didn't quite get through all the material, but that was expected with all the stuff going on in the world, but we got through a fair chunk of it, to be honest, for what went on. So here we go, last lesson on area under a curve. This is my favorite lesson in the sense of everything comes together in a really cool way, and it's area under a curve plus something called the fundamental theorem of calculus, like a pretty big one. It's kind of like in those movies, it's coming up to the final scene and then so many things are happening all at once and it comes together. That's kind of what today is. So here we go. So there's a lot to get through. So what I want you to consider is, for our purposes today, if you consider a area under a curve, what the area under a curve to us is going to be, it's going to be some function, and the area under the curve will be between two x values. Here in this case I've given 0 to 2, and the area under the curve would go to the x-axis only. It won't go below that for our argument purposes. And where this could be used in physics, for example, this could be, for example, let's say it was a velocity time graph. From your physics background, you should know the area under that curve would then represent distance. Or if it was a force distance graph, the area under a force distance graph from a physics point of view would represent work. It doesn't have to have a physical meaning like a physics meaning. It could just literally have the physical meaning of area alone. Maybe this is, I want to go and make a patio in my backyard that has a parabolic curve and I want to figure out how much surface area of cement I have to paint. Could be as simple as that. Now, what's going to happen, and I just want to show you the notation of where this came from. Originally when people did this, if the shape was relatively simple, this is pretty close to a triangle. So you could estimate this by saying the area could be half the base times the height divided by 2, and then you'd have a little bit of an overestimate. So that's one way that you could do it, but then you have overestimation. We want to get exact. So what people did was they took this picture and they'd break it up into a whole bunch of little bits, as much as they could, and then they draw these little rectangles for each section, and then they would add up all these rectangles. And obviously the more bits of rectangles that you made up, the better your approximation would be. Now here you can see I have a little bit of an overestimate, but the theory is you want the number of rectangles to go to infinity and the width of each rectangle to go to 0. So what's going to end up doing is you're going to end up adding up, and think about it for a minute, an infinite amount of widthless rectangles, which is then going to add up to a finite answer. Now, if you look at this just for a moment, if I just pick this particular instant here, let's say call this xi, and this would be like x1, x2, and so on, the height of this shape here would end up being the function evaluated at xi, and the width here would be a change in x, a very small change in x. And what would happen is you would have all these rectangles. For example, you'd have f of x1, which would be the height of this, times the change in x, plus f of x2 plus another change in x, and so on and so on and so on until you came down to the last rectangle. Let's call it xn. And then they decided, let's write this with summation notation. So they said I goes from 1 to n of f of xi delta x. And then they're like, well, we want n, we want the number of rectangles to go to infinity. So let's put a limit in front of here. Let's make n go to infinity. And then this over time morphed into this elongated summation, which is what that integral symbol stands for. So that really is just representing the infinite sum of widthless rectangles. This just turned into the function itself, and then delta x as n goes to infinity became the dx, like a really small part of dx. And that's where the notation for antiderivative came from. And then you might be wondering, well, why, if this is antiderivative, how does that link to area? And you're going to see today that antiderivative actually has a massive, well, it is the connection to the area under a curve, which you would have no clue. When I first did antiderivative, I was like, how does that lead to area? I would not have thought about that. But that's what's happening. And you can study all of this. You can actually do a whole bunch of summation work and find answers doing it this way. This is called, if you're interested, it's called Riemann sums. So Google that if you want some more stuff to do on Riemann sums adding up. We're going to do it from an antiderivative point of view. So here is our goal. Our goal today, and like I said, this is a pretty big lesson in a way, is to find the area under some random function. It could be a parabola, it could be a cubic, it could be anything we want, from some x equals a to x equals b, and this would be the area under the curve. We're going to get the exact answer. So that's our goal today. We want to find out what is this. All right, so here's the theory. So is there a better way of doing this without just adding up a whole bunch of rectangles? And yes, there is. So here's what I want you to consider first. Here's what we've talked about. Here's the function. Here's some area from a to x. Now I went, instead of from a to b, I went from a to x, so x can kind of move. I want us to assume, and here's the one assumption for any kind of proof. I want us to assume that there's some function a of x, an area function, that represents the area under f of x from a to x. So we have to assume that exists. Let's assume that exists, and then from there we can build what we want to build. So that being said, if I move a little ways away from x, for example, to x plus h, I can add on this really bad approximation to this extra change in area, which would be delta a, and that would be this area here. Now obviously there's some error here, but we'll get around that in a minute. So with that being said, the area function of x plus h, which remember that would represent the area from a all the way to x plus h, but the exact area. So the exact area from here to here, do you agree would be approximately equal to this area under that part of the curve plus this change in a? That's where it's not exact because there's a little bit of oversight here. All right, so here's what comes out of it. So watch carefully what comes out of this. So if I do this, would you also agree that a of x plus h minus a of x would be approximately equal to the change in area? So I just subtract that to the other side. Would have to be true. Okay. From there, you can then look at that and say, well, what is the area of delta A? Well, it's just a rectangle. What's the area of a rectangle? The area of a rectangle is base times height, if you want. And what's the base length? Well, this is x, and that's x plus h. This length here is h, so it's h times. What's the height? The height of that is the function evaluated at x plus h. So the area of that rectangle is this times this. And that's approximately equal to a of x plus h minus a of x. All right? Okay. Now, what I could do is I could divide both sides by h if I wanted to. And remember, h is positive, so I'm not being sneaky and dividing by a negative or something foolish. That's still a mathematical relationship that's true. And then you get something neat coming out. If you look at this carefully, that looks like something. And even more importantly, we want h here to get very, very, very small so there's no air. So if I make h going to 0, then this turns into an equals, because if h is approximately 0, then this is no longer approximately. They're pretty much equal if h is essentially 0. All right, this is really interesting. That is the that is the definition of the derivative. F of x plus h minus f of x over h as h goes to 0 is the derivative of f. But if I replace it with a, this is the derivative of a. And remember, this side I should have the limit as well. H goes to 0. As h goes to 0, what do we get? We get this equaling f of x. Now this is an amazing moment. It doesn't look like much, but this is the moment in the movie when there's that pause, or you can hear like this, like something's going on. We've just shown that this function, which we're saying exists, its derivative is the original function that we're dealing with, the area under. So even more importantly, here's where it's really cool, is to get the area out of this, I'm going to take the antiderivative. And the antiderivative of a prime is a. Then I'm going to take the antiderivative of this side. Now, one thing that you can do is I could write this many ways. At the moment, what I'm going to do, I'm going to call the antiderivative of little f big F, just for notation purposes. I could have even done this. Because remember we talked about that notation. I could have written that as well, but I'm going to call that big F for the moment. But remember, I have to put a plus c because there's always this constant that I got to deal with. So we've just shown that the area function here is the antiderivative of this function we're dealing with, which is really cool, plus some constant. But now that throws a thorn in our side a little bit because a constant we don't know, but we know some initial conditions. We know if you were to plug in a, big A of little a, the area between a and a would be 0. If I went from a to a, 0. So I know that the area from a to a equals 0, and I'm plugging a in for x. I can solve this for c. C equals negative f of a, which means the antiderivative, the negative antiderivative evaluated at a. So therefore, a of x equals f of x, big F of x, minus big F of a, as I replace that into there. And even more importantly, remember our ultimate goal was to find out the area between a and b. Well, that would be area of b, because remember this represents the area between a and b. This would be big F of b minus big F of a. And this is what we've now shown. I know it doesn't seem like lots, but this is huge. This is called the fundamental theorem of calculus. This says the area under little f of x from a to b, which is what this is going to denote now. The area under f of x from a to b, and they put upper and lower limits on there now, equals the antiderivative evaluated at the upper limit b minus the antiderivative evaluated at the lower limit a. And big F is the antiderivative of little f, and f is always considered to be continuous. So a lot of things happening there. First of all, without the upper and lower limits, that would represent an antiderivative. If I throw upper and lower limits on this, this is called the fundamental theorem of calculus, and this is called a definite integral. And you'll see in a moment how slick this is. Like, this is just amazingly slick. So here we go. So that first example that we had looked at, that we didn't do, find the area under this parabola x squared from 0 to 2. Here's what you would first of all draw the picture, which we've done. This is how you would represent it. This would say find the area under x squared between 0 and 2 dx. This will crank out that area, and here's how it does it. So what you do is you take this function here, you take its antiderivative. So the derivative of x squared is x cubed with a 1/3 out front because I need to cancel that out. So there's the antiderivative. You then draw a line like this and put a 2 up top, and that's a 0 down below to carry with these. And here's the fundamental theorem of calculus. I'm going to evaluate it at the upper limit, subtract it from evaluating it at the lower limit. So literally, you plug 2 into this. That's big F of b, so to speak. And then you plug in, subtract it from the lower limit. That's big F of a. And then out of this comes the answer, which represents the exact area. So this gives me 8/3 minus 0, because 0 cubed times 1/3. And you get 8/3 out. So the area under the parabola from 0 to 2, the exact area, is 8/3 of a squared unit, which is really neat. If you happen to have a graphing calculator, you can do it on Desmos as well. We have to fart around a little bit more. If I went to a graphing calculator and graphed x squared, let me make my proper window, zoom window, I'd get my little parabola there. Maybe let's make the window a little better so it's not so squished. That's a little better. Okay. If I wanted to find the area from 0 to 2 underneath that graph, one thing I can do underneath the calc, so I go second calc, down the list, you see there's an integral number 7, and then it says lower limit is 0, upper limit was 2, and then it'll paint the picture and tell you what the area is, 2.66666, which is 8/3. You can do it with Desmos as well. You just have to go and look for the integral symbol in the miscellaneous functions. Alright, so next few here. Find the area under sine x plus 1 from pi over 2 to pi. First thing I would always do, because they're going to give you this probably first, draw a picture. There's sine plus 1. Took me a little while to remember, oh, it's just a sine graph moved up 1. And they want us to do the area between pi over 2. It's always this vertical line to pi. And we want to find out that area always to the x-axis. Now, we're not going to get into great detail what happens if it's below the x-axis or what happens if it's a split between the two. You can get into more detail with that, which as the course goes on, and you definitely will, but not here. So how do I find that area? Well, notation-wise, it's the integral of sine x plus 1 dx from lower limit pi over 2 to upper limit pi. That setup represents this area. And then now how do you go about doing that? Well, you take the antiderivative of this function. So the antiderivative of sine, we did it a few times, is negative cosine. The antiderivative of 1 is x. You draw a bar for the upper limit and lower limit. And then you are literally going to evaluate this antiderivative at the upper limit. So there's the upper limit evaluation at pi minus the lower limit evaluation. And whatever this value is minus this value, that is the area under that curve, which we could figure out now, because remember, cos of pi is negative 1, so it's negative 1 plus pi. Cos of 90, or pi over 2, is 0. And then just be careful with my symbols here. I get 1 plus pi minus pi over 2, which is 1 plus pi over 2. And that is the area under that curve. You can change that to a decimal if you want, for those engineers out there. So 1 plus pi divided by 2, 2.5707, blah, 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 blah. Units squared. Really cool. If you try to do that by estimate, you can get a close estimate by breaking it up into triangles and rectangles, but that's the exact, like right down to the millionth, quadrillionth decimal place. Last one. So, find the value of this. Now, again, what is the meaning of this? Because it has upper and lower limits, this is going to be a definite integral. It's going to represent the area under this curve, which is a rotten curve, between 9 and 7. Now, I guess I could graph that. What does this graph look like? E to the x, oops, e to the x plus x squared. Really weird graph, and I'm gonna have to do the window. My y has to go really high because this thing's growing like you wouldn't believe. That's probably not even enough. There it is, okay. And then if you found the area between 7 and 9, I don't even know if that would have enough growth on it. I don't think it does. I have to make this really, like, it's such a steep graph. E to the x grows so quick. So here we go, it's going to grow. Oh, that's a little bit too much. Maybe I got carried away. But I can take 1 0 away. And I can find now the area with my calculator with integrals. I can just go second trace, integral button number 7, lower limit 7, upper limit 9, and this will crank out the area. There it is, 7,135.11, but we're going to do it exactly. So how do you evaluate this? You take the antiderivative. What's the antiderivative of e to the x? Well, that's e to the x. What's the antiderivative of x squared? Must be a 1/3 x cubed. And then I'm going to evaluate it at 9 and 7. So evaluating it at 9, it's e to the 9th plus 1/3 times 9 cubed minus evaluating it at 7. And that's just a rotten number. You wouldn't be able to do much to that except for just clean this up a little bit, but cheating a little bit. There's the actual value if you want to evaluate it. But there's the exact answer. It's beautiful. Okay, the next one. Without a calculator, I should be able to even graph this and visualize what it's asking. It wants the area under sine between 0 and 2 pi. Now here's where it's interesting. For here, it's above. Remember, going to the x-axis. Here, it's below. Any thoughts on what's going to happen to these two areas? Let's just see. So, take the antiderivative. The antiderivative of sine is negative cos. Evaluate at 2 pi and 0. So evaluate at 2 pi, subtract it from evaluating it at 0. What's cos of 2 pi? I have to think about my cos graph. Cos of 2 pi is 1, so this would give me negative 1 minus, oh, don't forget the negative there. Got to put a negative, okay. And cos of 0 is also 1, so I have negative 1, so it's negative 1, take away negative 1, which is 0, which is interesting. So the representation of this to the mathematics is above the x-axis represents positive, below the x-axis represents negative, and so when you add those two areas together, you get an overall net of 0. Now, if you wanted to work out the true area, like the amount of paint it would take to paint that, you'd have to work out the area from 0 to pi, work that out as a value, and then double it because of symmetry. Or work out the area from pi to 2 pi and add the two together. All right, so if this was a physics question, this was force and distance, this 0 would be representing like 0 work. You've done positive work here and negative work there. Or if this was a velocity time graph, this would represent 0 displacement, so to speak. All right, so that is antiderivatives. Lots of stuff, like big stuff here, like huge. And then now this takes off into a whole branch that you can just kind of do this over and over and over with many things: area between curves, volume, surface area. It's just, it goes on and on and on. It's awesome. All right, have a good day. Over and out.